So I know some of you may select chemical engineering as your major in your sophomore year. So today's talk, I will briefly introduce my job and to let you have some understanding to the future of chemical engineering. Okay, so beginning, let me introduce myself a little bit. I graduated from National Taiwan University Chemical Engineering Department last year, 2022. And after that, I just joined our CY group to be a researcher until now. So I have about 1 year's working experience. And I have some expertise in chemical engineering related to the process modeling, optimization, control, and design. Besides, I have some experience in greenhouse gas emission reduction management. Later, I will explain this content a little bit so you can understand that more. Okay, so before jumping into the main content of today's talk, let's have some interaction. I have 2 questions for you. The first question is, I want to know, do you have experience in doing chemistry experiment before studying NTUST? Maybe in your senior high school, junior high school. If you have such experience, can you raise your hand? Before joining NTUST, did you have experience in doing chemistry lab? Okay, so just maybe 2 or 3 of you. That's fine. If you have such experience, later it might be easier for you to understand what I'm saying, but if not, I think that's fine. Okay, the second question is, I know for this course, after my talk, if you raise your hand and ask me a question, you can get credit. And I have talked to your TA. So next question, if you answer my question, you can also get credit. Okay, so my question is, just tell me your understanding and imagination about what chemical engineering is. I heard someone say want to speak Chinese, but is that okay? I don't know the rule of this class. If a student can speak Chinese or not. Okay. Okay? Okay, okay. Then okay. Go ahead. Your TA said okay, that's fine for me. Okay. Okay. 你要直接讲you want to speak what you are understanding? Okay, go ahead. Don't be shy. 不要害羞啊。加分呢
OK， 不用拿麦克风，随便你。就是化工比较，就是注重实作嘛，然后化学就是理论派，然后化工就是比较讲求一些效率，就是因为有一些太理论的东西，其实我们达不到，所以他会对注重效率。然后很多人会觉得化工什么化学的比例比较重，但它其实物理的比例会比较重一点，这样子，我的认知。
OK. Okay, let me briefly translate that. So the classmate said he think compared with chemistry, the chemistry is more theoretical, and for chemical engineering is it's more practical, and we can do something real in the world. And also he think that when hearing about chemical engineering, someone may think that it's mainly about chemistry, but the content of physics is actually very large in the chemical engineering department. Okay, that's the student's idea. Well, anyone want to share your imagination or idea? Come on, get credit. Okay.
I have the same idea as him, unless I think chemical engineering is more about so with chemistry you do it in the lab, but chemical engineering you more scale it up, you apply it in factory settings and you calculate the sort of failure factor, what will fail when you scale it up, so you make it big, you make it more practical.
Yeah. Okay, thanks. Yeah. Actually, it surprised me that you almost say the answer in my mind. Yeah. Okay. So that's my brief description on what chemical engineer's job. Okay. I think the first student said it is correct. Actually, we have lots of physics in chemical engineering because we want to know some, and for example, most for the fluid, because in chemical engineering we deal with lots of things related to fluid or say the liquid and the gas. So that's correct. And that student, the answer is, I think it is perfect. So actually, the main idea of chemical engineering is to scale up something from there to commercial scale. So that's what I said. For example, if we are going to develop a new product, and the chemist and the material scientist, maybe they can produce something new by following some process inside the lab. But for our chemical engineer, we have to scale up then from lab scale to a commercial scale. Because you can imagine for a company, the main target is to make money. So if you cannot make the product be sold and make lots of money, that is a failure project. Okay, so and that student also use a very good term called scale up. Yeah, we will say that process scale up, and this is a core of one of the core of our job. So I will introduce an example later. Okay, and besides, chemical engineering industry is a greenhouse gas intensive industry. That means the industry emits lots of the greenhouse gas, and this will lead to severe global warming problem. And due to some regulation and policy, the industry has to pay lots about the GHG emission. So we have to work on to reduce the emission, and I will explain the idea and what I'm doing in my job later. Okay, so let me begin with the case of a process scale up, which is the production of a valuable human nutrient. So this nutrient is good for eyes, skin, and cardiovascular, your blood vessel and your heart, good for this health. And I can, due to some confidential issue, I cannot tell you what this nutrient is, but I can tell you that the market price is about $5,000 per kilogram. That's a very high value. Imagine, this is my bottle. It's weighed about 500 grams. So 2 bottles of these things cost $5,000, about 150,000 Taiwan dollars. It's very expensive. So we want to make lots of money by producing this product. Yeah. Okay, and the chemists in our group have found a method to produce this nutrient in higher production rate by fermentation. In Chinese, 发酵. Okay, the idea of fermentation here is to let certain species of yeast to consume edible oil under specific condition. And the yeast can produce and store the nutrient we want inside cells. So you can see schematic here. This is a fermenter with an impeller inside. The impeller is something will rotate and mix everything up inside the fermenter. And in the fermenter, there will be liquid fermentation media, edible oil as the liquid phase, and the yeast cell as the solid phase. And the cell stores the desired nutrient we want. So the question is, okay, the chemist developed such a process. The question for me is, how to get the nutrient from fermentation growth? To do that, we develop a lab scale process to get the nutrient. So the first step is we use centrifuge to separate the liquid and the yeast cells. If you are not familiar with the centrifuge, that's a machine. If you put things into the tube, it will spin very fast. By the centrifugal force, the yeast cell with higher density will deposit in the bottom of the tube. And on the top, there will be the liquid. So we keep the cells here, and we discard the liquid. Next, we mix the cells with some liquid chemicals. We call that solvent. If you are not familiar with the term, let me give you an example. For example, if you put some you put some sugar inside water and dissolve it. Then we will say this is a sugar solution with sugar as solute and the water as solvent. So by the analogy, you can know that we use some solvent to mix the cells, and the solvent can dissolve the nutrient, so the nutrient will be the solute. And this process is called solid liquid extraction in chemical engineering. Okay, next we do centrifuge again to separate the yeast cell and the solution. But this time we keep the solution and discard the cell because in this time cells does not contain the nutrient we want. The last step is to evaporate the solvent from the solution. In that, we can do that by a rotary evaporator. Okay, so the idea of rotary evaporator is if we put the solvent inside the evaporating flask, and we reduce the pressure inside, or say a vacuum. In this case, if you are familiar with some physics, you will know when the pressure decreases, then the boiling point of liquid will also decrease. In that case, the liquid or say the solvent evaporate, become a vapor. After become a vapor, they will go to the main condenser. In the condenser, there is internal coil. Inside the coil, cooling water is flowing. So when the vapor contacts the outside surface of the coil, it will be cooled down and back to liquid again, and to be received in the receiving flask. So by doing that, you can evaporate all the solvent and to get your the final product. Okay, so after evaporating all the solvent, we can get the final product, which contains some lipid components come from the yeast, and also the nutrient we want. So we will have this kind of dark red, very viscous, sticky liquid. That's our final product. And as for the solvent, we recover lots of solvent here, but because this solvent contains some water from the yeast cell, it will affect the extraction efficiency later. So in that scale, we just discard, put that solvent away, and to finish our process. Okay, that's the lab scale process. So I believe if I give you the instruction, all of you can duplicate that in that. That's not the difficult task. But the problem is how to scale up the process from lab to commercial. Okay, by completing the fourth step I stated previously, if I take 1 kilogram of the fermentation broth, we can produce 10 grams of the final product, so about 1%. But my boss told me, hey, Johnny, please design a process to produce 10 metric tons per batch. Okay, so you know that 10 grams to 10 metric tons is a 1 million time difference. So, and to do this, some of chemists and biotechnology scientists in our group said, oh, that's easy. You just multiply everything. The amount of feedstock you required, something you require by 1 million times, and just go buy the equipment from website, from eBay or from something like Taobao. That's it. Very easy. But as the chemical engineer, we know the problem is not so easy as they imagine. So I listed some challenges on the scale up, and believe me, that's just a little bit part of the challenge I am facing with. So the first thing is, what's the proper size and type of equipment? Imagine you cannot have a lab scale centrifuge or rotary evaporator to do the such a commercial scale process. And also, we must recycle a solvent, otherwise the amount of solvent consumption is too large. So we have to think about how to recycle that. And also, when we are going to build up the plant, we have to cost lots of money. We have to make our boss agree to pay that money. So we have to make a good estimation on the plant construction cost. That's some of the problem I'm facing with. So let me introduce how I do that briefly. Okay, the first step is to plot a thing called blood flow diagram, or say BFD. The idea of BFD is to show the main operation and the main strings on one plot. That is to let us to have a good overview to the process. So you can see, basically I just plot the 4 step I mentioned in previous slide to become the block flow diagram. But add one thing, that is we have the solvent purification and recycle solvent in the solid liquid extraction part. After that, we will do the mass balance calculation. So what's the mass balance calculation? The idea is to calculate the amount of material and composition of each stream based on experimental data and some estimation. That is to know the amount of feedstock required and the information for sizing the equipment, or say to estimate how much the equipment should be. Okay, so I listed some algebra here. The test for us is to calculate this algebra out. So I will not go through the detail, but I can show that's how the final calculation looks like. So I do that in Microsoft Excel. You can see there are lots of block cells and lots of lines to do the calculation. Yeah, you can imagine that's a very tedious and complicated process, but I have to do that. Okay, the next problem is the design of the solvent recovery process. As told before, we have to do that in commercial scale, but we didn't do that in the lab scale. So how should we decide that if we don't do the experiment? Okay, let me introduce one method that is common to separate liquid mixture in chemical engineering. This is called distillation. The idea is to separate the liquid mixture based on the difference in boiling point. And let me give you an example of daily life. That is strong liquor. I know in Taiwan, if you are older than 18 years old, you can drink alcohol. And I believe some of you have tried that. Yeah. So, for example, the strong liquor contains something like vodka, gin, rum, tequila, whiskey. All of them are strong liquor, right? Some is nothing, so you have to try that, of course. Okay. And this strong liquor, they will have alcohol purity larger than 40%. The alcohol is actually ethanol. In chemical engineering, we say ethanol. Okay. When I was a freshman in university, I joined cocktail club. In the club, the teacher told me that actually this strong liquor are made from fermentation also. But by fermentation, the ethanol concentration can only reach at most about 20%. Otherwise, the yeast cell will die. So we cannot get strong liquor just by fermentation. So the problem is how to do that to get a strong liquor. So ethanol has a boiling point about 80 degrees Celsius at atmosphere. If we're heating up the mixture, the ethanol will evaporate faster because water has boiling point about 100 degrees Celsius in the atmosphere. So we're heating up the mixture and more ethanol evaporate, and we condense the vapor, we can get a strong liquor. And that's a daily life example of using distillation to separate the liquid mixture. Okay, talking about the case in chemical engineering, we use distillation columns to separate the solvent mixture. So this is a schematic. This is a column, or we say tower. And there will be a feed. Feed is something we have to separate. In our case, will be the recovered solvent. And inside the column, there are lots of trays. This is to enhance the liquid vapor separation. In the bottom, there is a reborder. The reborder is to heat up the liquid to evaporate them again for the further separation. In the top, we will have the condenser to condense the vapor back to liquid, and some of the liquid will reflow back to the column, or we say reflux. And that's for further increase the purity. And some product will go out as the distillate product. So that's something we are commonly used in chemical engineering to separate the liquid mixture. But the experiment is not easy to do in the lab, so we will use computer simulation instead. We have some commercially available software to do the simulation. And to run the simulation, we have to know the principle of distillation well, and the mass balance idea as well to run the simulation. So that's also a core capability for our chemical engineer. Next is talking about the equipment sizing and selection. First, we need some vessels and tanks in our process because these vessels or tanks have to store the feedstock, the nutrient solution, the recovered solvent, and so on. And also, when we are doing the solid liquid extraction process, we have to use a vessel to do that. But the question is how large these vessels and tanks should be. If too large, then we take up lots of space and higher cost. If too small, we cannot make the desired production rate. We have to consider the material for construction also. We may use carbon steel, stainless steel, fiber reinforced plastic, and so on. That depends on the stored material, regulations, cost, and so on. So we have some experience rule or some equations to do the sizing and the material selection. I will not go through the detail, but I have to do that. Okay, and also for centrifuge, actually there are many types of centrifuge available. We have to select the type which is most suitable for our process. For example, we definitely cannot use the lab scale centrifuge to do that. We want a centrifuge that can run continuously, so that we can minimize the manpower required. And we know that the selection depends on the solid phase and liquid phase density, solid particle size, liquid viscosity, and some other parameters. But I have to say, I myself is not an expert in centrifuge. So this time I will collaborate with vendor to understand which type of centrifuge is the best for us, and to do some test, some calculation based on their input. So that's a collaboration progress. As for the evaporator, again, you can imagine we cannot use a very large rotary evaporator inside the commercial scale plant. So the question is how to achieve such a high evaporation rate in commercial scale process. Okay, the key is to increase the heat transfer area. So they introduce one kind of equipment that is suitable, which is the falling film evaporator. The idea is to put the nutrient solution from the top of the evaporator, and they will flow into many tubes, small tubes, and the liquid will flow inside the tubes. Outside the tubes, we use steam. The steam, I think you can get the steam by just boiling out the water. This is the steam. And the steam can be used to heat up the solution inside the pipe. After that, the solvent inside the pipe evaporates and will be condensed and collected. And in the end, we will have our final product. After evaporating all the solvent, we will get the final product in the bottom of the evaporator. Okay, so if we clarify all the equipment we want, then we can draw a thing called process flow diagram, or say PFD. The PFD is a flow chart that can show us the relationship between the major components at the industrial plant. So you will see lots of the line connection, what's the connection, what's the flow of material from one place to another place, from one equipment to another one. Yeah, and also we have to consider the equipment for material transportation. For example, we use pumps to transport the liquid. They have to be included in the PFD, so you will have a complicated drawing here. And after the drawing, we can list the equipment we want or say we need. And by using this list, we can write down the information and then some specification of the equipment on this table. And the list can be used for the cost estimation and the valuing, quote, design, procurement, and construction process. Okay, I take about 20 minutes to explain this part, but actually for the process design and scale up, this is just the beginning. We have to do lots of things later. For example, we have to consider the detailed design of each equipment and the piping design. The pipe is we want to transport things inside the pipe, so we want to design a pipe properly. And also we have to consider the instrument for process monitoring and the control, and also the control loop and logic. For safety issue, we have to do the hazard analysis to consider what's the possible hazard or say dangerous things inside the process. And for the equipment, we have to consider the mechanical design. And when building up the process, we have to consider the civil engineering knowledge. So as a chemical engineer, I cannot know everything very well. I cannot be expert in every aspect. So we have to collaborate with civil engineers, electrical engineers, and mechanical engineers. That requires a lot of collaboration. Okay, in this example, I just say we just scale up from lab scale to commercial scale. But actually, for most of the process, we need a thing called pilot plant. The pilot plant is the scale between the lab scale and the commercial scale. Otherwise, if we just scale up the process by too fast, we may encounter some operating problem or some problem like the product spec is not qualified. So sometimes, for most of the time, we require a pilot plant. Okay, that's the introduction for the process scale up. And the next thing, part I will talk about the introduction to greenhouse gas emission inventory and the emission reduction project. Okay, I think all of you have heard about that, but let me give some review. That is the greenhouse effect. The greenhouse effect is actually some component inside the atmosphere will absorb the energy from sunlight and keep the energy near the ground. So thanks to the greenhouse effect, the surface temperature on the Earth is maintained habitable for living beings. That is good. However, the greenhouse effect becomes too strong because human beings emit lots of the greenhouse gas, and this causes global warming problem. And the greenhouse gas include the most famous one, carbon dioxide. But actually, there are some other gases like methane, the nitrogen oxide, and the chlorofluorocarbons, CFC. The CFC will be used in the refrigerant in the air conditioner. So actually, these are all the greenhouse gas. Okay, so why to reduce the greenhouse gas emissions is important? If we look at the viewpoint of environment, is to mitigate the global warming problem. The global warming problem leads to climate change, sea level elevation, species extinction, and so many other severe problems. So at the United Nations Climate Change Conference, there was a thing which called Glasgow Climate Pact. The idea is to do the reduction plans to try to keep the global warming within 1.5 degrees Celsius. Because someone is report that if we don't do the greenhouse gas reduction, in 2050 we may have the temperature, global temperature, 2.5 degrees Celsius higher than the pre-industrial time. So that's the reason why we have to reduce the GHG emission in viewpoint of environmental protection. But for a company, another thing we have to be careful about is the viewpoint of commercial. That's because there are some policies we are going, the company will go pay for carbon tax and carbon fee. Okay, for example, the carbon tax is imposed on the product. It is based on the greenhouse gas footprint during the production. As for the carbon fee, it's imposed on the business organization based on the total emission by the organization. So no matter how, if the company emits lots of greenhouse gas, we have to pay lots for the carbon tax and carbon fee. You can see there are some working policies by the European Union, by the United States, and also by the Taiwan government. So if a company cannot reduce the GHG emission, then lots of carbon tax and carbon fee will be imposed. That will affect the company's revenue. And also, if a company can reduce lots of the GHG emission, that will be good to enhance the reputation of the organization. So that's why we have to do that. Okay, here I list the procedure of running the GHG emission reduction project. So the first one is we have to do the greenhouse gas emission inventory. This part is to identify the emission source and calculate how many greenhouse gas are emitted by our company. Next, we will set up the emission reduction plan based on maybe some policy from government and some international initiatives. And also, next, we will draft the GHG emission reduction actions to think about the possibility of GHG emission reduction. And finally, after we plan that, we will do that. But before doing that, we have to think about the amount of emission reduction, the cost, and the technical feasibility. So I will go through this process. Okay, in the beginning, let me introduce why chemical engineering industry emits lots of the greenhouse gas. So actually in Taiwan, the chemical engineering industry accounts for about 20% of the nation's total GHG emission. And for the emission, the first part is the direct emission from the process. For example, we burn fuel. For example, we emit the exhaust gas from the process. And then we use refrigerant in the air conditioner. These all of them are the direct emission of greenhouse gas from process to the atmosphere. Another kind is called indirect emission. For us, that's the consumption of electricity and steam. Because they are purchased outside the company. So the emission is actually outside the company. But we use that, so we have to account for the emission by using the electricity and the steam. For electricity, you can imagine we use electricity because we have to use some transportation, for example, pump. That's to transport the liquid. The compressor is to transport the gas. And we also have to run the control system, so that requires lots of the electricity. As for steam, we have a minor use, that is to directly inject steam into the process. But we have a major use. Okay, that's time for us to interact again. Can you guess what's the major use of steam inside a chemical plant? Okay, again, if you raise hand and make a guess, you can get credit. Yeah. Just guess that. What's the main usage of steam inside chemical engineering plant? To heat? Okay. To produce energy? Okay. Other answer? Okay, both of you are correct. But mainly I will say to produce heat. Yeah, produce energy, kind of, but you can also think about heat as an energy. So you can say to provide heat energy. So I think both of you make a good call on that. Okay, so in my turn, I will say steam is a very good heating medium. The heating medium means that the steam will not contact with the thing you are going to heat up, but it just transfers heat or send heat energy from steam to the thing you want to heat up. So earlier I explained the evaporator for the nutrient process. That's an example. And the distillation column is also an example because we know in the bottom there is a reboiler to heat up the liquid, and that requires steam. Okay, but some of you may ask, if you want to heat up something, you want to evaporate something, why cannot we just burn fuel in the bottom or inside the reboiler to evaporate the liquid? Okay, the reason is if you're during burning fuel to heat up the liquid, we will face a problem that is the temperature is unnecessarily high. By dirty burning, the temperature may rise to hundreds of degrees Celsius or even 1,000 degrees Celsius. That requires the special type of the equipment, so that will increase the cost. We don't want to do that. And also, burning some fuel, for example, if you burn coal burn coal, then it will emit lots of the pollutant. Then in this case, you will have to set up additional pollution control system to capture the pollutant. Then that's not a good idea to do that. So usually we use steam to heat up most of things inside the chemical engineering plant. Okay, knowing the emission source, the next question is how to calculate the GHG emissions. Let me give you two examples to just make you have some feeling. So, for example, if there is a plant emits 1,000 tons of exhaust gas with 20% carbon dioxide inside and 0.1% methane inside, then we can calculate, okay, we emit 200 tons of carbon dioxide and 1 ton of methane. However, it is reported that methane has 28 times of global warming potential than carbon dioxide. In that case, we will express the total emission by the equivalent carbon dioxide emission, or say CO2e. In this case, we will have 200 tons carbon dioxide and 1 ton of methane, but this is 28 times stronger than carbon dioxide. So the total equivalent carbon dioxide emission will be 228 tons. Another example is if we buy some electricity from Taiwan Power Company, and the Taiwan Power Company announced the emission of the when generating the electricity, then we just multiply the factor and the amount of electricity we used, we can get the final answer. So actually, it's not a very difficult calculation, but when we collected the data from one point, we have to consider lots of calculation. So we have to identify all the emission source and the corresponding calculation to do the GHG emission inventory to get the final emission of a result. Okay, next is to set up the GHG emission reduction plan. So this can be based on, say, Taiwan government's idea. For example, Taiwan government announced that compared with the base year, or say 2005, we have to make 10% emission reduction in 2025 and 20% reduction in 2030. So our company, LCY, can follow the government's target to set up our target. But the question is, how do we achieve that? Okay, to achieve that, we have to consider some action items for the GHG emission reduction. So I list the 3 kinds of action we can do. The first one is the equipment replacement. The idea is, imagine if your air conditioner is very old, say 10 years old, 20 years old, the efficiency will decrease as the the efficiency decrease as the time passes. So if you can replace the old equipment with the new equipment, then we can get better energy efficiency. That means the less GHG emission. And also some new technology can lead to higher equipment energy efficiency. So that's also a reason why we can do the equipment replacement. The second part is to purchase the green electricity. This refers to electricity generated from renewable sources, including the wind energy, solar energy, hydro energy, geothermal energy, and so on. The third one is called process revamping. That is to modify the process to reduce the direct emission or energy consumption. Another sort of thing, I think the most difficult part for you to imagine is the process revamping. So I'll give you two examples. The first example is the tail gas combustion. Okay, tail gas can refer to the gas that is not the main product and emitted from the chemical engineering process. For example, some gas will release during fermentation that can be treated as a tail gas. And after combustion, we will have some tail gas. And the combustion means to burn out something like that. And also, after the chemical reaction, we will emit some gas that also can be treated as the tail gas. So, in our solar group, there is one plant that generates tail gas containing about 50% of ethylene and propylene. If you are familiar with the chemical formula, you will know that both ethylene and the propylene can be combusted and generate lots of heat. Previously, the tail gas is treated as an exhaust gas and just burn up and that's it. But now, after the process revamping, we combust the tail gas and generate heat. And this heat is used for further steam generation. In that case, the amount of the purchased steam can be reduced. That means greenhouse gas emission reduction. The second example I will show you is the heat integration. So in a chemical plant, there will be lots of the stream need to be heated up, and lots of stream need to be cooled down. To heat up, we can use steam. To cool down, we can use cooling water. But what if we match the stream to be heated up and to be cooled down? So for example, if there is a stream, we want to cool down the stream from 100 degrees Celsius to 80. And another stream, we want to heat up from 30 degrees Celsius to 50. Then that's a match. We can use a heat exchanger to cool down this stream and also heat up this stream at the same time. So by doing that, we can use this steam and cooling water for the cooling and the heating. And that's also an energy saving and a GHG emission reduction. But of course, we require additional heat exchanger to do that, so that means additional cost. That's something we have to consider before we make things into real. So when doing every actions for the GHG emission reduction plans, we have to consider the amount of GHG emission reduction and the investment cost. Because if we spend a lot of money to reduce GHG emission, our boss will be unhappy. He will blame me. And also, there is a trade-off between the GHG emission reduction and the cost. And also, we have to consider the technical feasibility. For example, if we want to install a new heat exchanger inside a plant, the problem is there enough space for installing a new heat exchanger? That is something we have to think about. Okay, so in the very end, I introduced part of that job for process scale up and the greenhouse gas emission control. In the end, I will briefly introduce my company, LCY, because I represent that for the presentation. Well, so LCY Group, 李长荣集团, is a worldwide company. It founded in 1950, so we already more than 100 years. And we have business unit and production sites around the world, including Taiwan, the mainland China, Canada, and the United States. Okay, this is where I come from, the R&D center in Kaohsiung, southern Taiwan, in Kaohsiung. And this is the building. We have some office, lab, gym inside the R&D center. And in front of the R&D center, there is a pilot plant. The pilot plant is what I just talked before. That is, to the scale up, we have to do things in that scale first, then pilot scale, then commercial scale. So inside the pilot plant, we will do some tests in a larger scale compared with the lab scale, but smaller than the commercial one. This is what our R&D center is like. So we have a good lobby, a coffee room, a gym, the rest area, and this is our experimental lab. So you can see they are very clean. It's a good place to work in. I think that's good. And then for our R&D center, we have four major groups: engineering science, material science, chemistry science, and analytical science. So for me, I'm from engineering science. We do the process engineering work, we do the scale up, the process design. And if you select the material engineering in your sophomore year, you may join our material science group. There will be lots of chance for you to join us. In the end, the outside group will also provide some scholarship. You can log into the LCY Education Foundation's website. There are lots of the scholarship for the master student, for PhD student, but they are too far for you. But we have some outstanding student scholarship activities. They also provide a scholarship for undergraduate students. So you can click into the foundation's website to see whether there is a match for your condition, and you are welcome to apply for the scholarship. Yeah, okay, that's all of my presentation, and thank you for listening. If you have any question, you raise your hand to get your credit. And also, if you have further more questions, you can ask me after the class, or even send me an email. I am willing to reply to you. Okay, thank you. 现在就进 Q&A 时间了。Okay. Okay, so yeah, Q&A time.
So, if anyone asks a lecturer question, I will give you extra points, and which will account for 1 point of the total score. So, go ahead.
Just 1 point? Please.
Still don't really understand how refining process can reduce I still don't understand how refining process can reduce the greenhouse gases produced by that process.
Okay, so your question is why revamping the process can reduce the greenhouse gas emissions? That's your question. Okay. Okay, so my answer is I take the heat integration for example. Yeah. Okay. Oh, okay. Okay, 好. Okay, that's fine. We go. Okay. So, for example, let me introduce again. So, if we have a string need to be cooled down, and one stream needs to be heated up. By what we have said before, if we want to heat up a stream, say this one, we require some steam to heat up that. But when we use steam, the steam is generated outside the company, and to generate steam, it requires energy. So we needed some energy to heat up this stream by either steam or by other method. If in our process there is a stream need to be cooled down, say from 100 to 80, then we can try to use the energy here. Because when we want to cool down something from 100 to 80, it releases energy. Does that make sense to you?
So we use the heat that we want to cool and
Yeah.
to heat something else.
Yeah, correct. So yeah, when a stream reduce when temperature of the stream reduce, it releases energy, and this energy can be used to heat up other stream. In that case, we can use less steam to heat up the material. That means the energy saving, and the energy saving means greenhouse gas emission reduction. Okay, if that's not clear, we can talk about that later. That's fine. Right, all right.
So you said like there is a pilot plant in the middle, right? So how big of the difference between the lab and the real project that you need to initiate the pilot plant?
Okay, so the question is how large the pilot plant is. Okay, it depends on the process, but let me give you an example. So another project in our company is in that scale, it produced about 200 grams of polymer every run. But in pilot scale, we produce about 10 kilograms. So 200 grams to 10 kilograms, about 50 times scale up. And our final target might be 1,000 kilograms per run or even higher. So the scale up ratio depends. It's different from process to process, but you can imagine, say about I will say at least 10 times, or even 100 times.
I want to ask you about what is the job expectancy of the chemical engineer in the job market, especially in the developing country. You mean like the percentage of getting the job, how big is the job opportunity in chemical engineering, especially in developing country?
In the developing country, okay. If you are talking about the developing country, I think that's for other country I'm not familiar with. But if you are talking about the chance of working at chemical engineering, related company in Taiwan, if you study chemical engineering, I will say, for my experience, my classmate, maybe say 40 to 50% student will join the chemical engineering related company after graduation. And I have to say, in Taiwan, most of the graduate students from chemical engineering will go to semiconductor industry, say TSMC or some other related company. But if you're talking about other countries, I have to say I'm not familiar with the condition. It depends on the national situation. Okay, any other question?
was wondering that in the first example that you gave us, you told us that the chemical engineering use bacteria to synthesize a certain nutrient. Is chemical engineering still reliant on bacteria, on using living creatures to synthesize most of the chemicals, or can the industry produce a lot of them synthetically?
So you mean specifically to produce the chemical, or
can the chemical engineer also produce process to get over the reliance on bacteria and other living creatures to produce certain chemicals?
You mean to reduce the rely on some other stuff, or
How reliant are the industry on using bacteria to synthesize?
Material? Okay. So the question is how the industry rely on bacteria to do synthesis. Okay. I have to say that for the nutrient I introduced, previously there are two main sources. The first one is to extract and to just extract from the natural good. For example, from some food or from some algae, something inside the water. Yeah. And then another one is to do the synthesis by chemical synthesis, to do lots of the organic chemistry work to do the synthesis. And for using the bacteria, I know some of the commentators are doing that. Not many, but some of them are doing that. So that's that's a chance. And I have to say, because I'm not familiar with that kind of fermentation, or say the process to use bacteria or say the yeast cell to produce the nutrient we want. So I don't know how the possibility or say how the development will be. But I think that should be possible. Okay. Okay. Any other?
Thank you for your lecture. And I have two questions. And my first question is, does the company require a bachelor degree in chemical engineering if you want to become a chemical engineer? And my second question is, if they do require, do you think it is necessary?
Do require. Okay. So I think the question is what's the requirement for your scholar? Okay. Take our company as an example. If you study chemical engineering, that's of course that's possible to join us. But if you are studying materials science, material engineering, and maybe something like chemistry, I think it's still possible. As you can see, our group has some other department related to material, to chemistry. So if you're talking about whether we have to study chemical engineering to join our group, I will say not. You have other choice. But the degree is necessary. I think a bachelor degree is basic for that, because after getting the bachelor degree, you will have the basic understanding to this field. So I think that should be necessary. Yeah. And I think that's also the answer to your second question. And I have to be frankly speaking, that is for our company, and especially for the department, for my R&D department, most of us are masters or even PhD, because we may need some ability to design experiment to come up some new idea, and that's the training inside the graduate school. So for our case, that's it. But there should be some other work and doable if you have the bachelor degree. So yeah, that's also a possibility. Okay, any other question? Okay, if not, then that's it for today. Tia, do you have any other thing want to say?
No.
No. Okay. So I can announce class dismissed. Okay. Bye bye. Okay. If any question want for me, just come here and then we can have some discussion. Yeah.